Hey everybody, just want to welcome you to Module 2, Lecture 1. In this week, what we're going to be taking a look at is the relationship to thermodynamics, how heat transfer relates back to thermo. And within this module, we're going to take a look at the conservation of energy, a couple different applications, one being the application to a control volume. We're also going to take a look at the surface energy balance and talk a little bit and review the first and second laws of thermodynamics. So as this relates back to your textbook, this is chapter 1, section 1.3 is where we're going to start. So now I want to take some time and discuss the relationship to thermodynamics. So in this module, we're going to discuss how there are similarities and differences between heat transfer and thermodynamics. So even though there's a lot of similarities and some complementary parts between these two, there are some fundamental differences. So if we think back to when you took your thermodynamics course, we know that heat transfer did play an important role in your first and second law of thermodynamics. And the reason behind this is because heat transfer is one of the primary mechanisms for energy transfer between a system and its surroundings. And this right here is really important, even though it's a simple phrase here, between the system and its surroundings. And we'll see that a lot in lecture today and some of the example problems we go here where we're really interested in exactly those things. How does the system that we're looking at relate? What are the surface temperatures? How do those relate to the surrounding temperatures, the environment around it, and how does that come into play with heat transfer? So thermodynamics may also be used to determine the amount of energy in the form of heat for a system to pass from one state to another. So that was one of the main things that you guys focused on within your thermodynamics class. But it did not consider the mechanisms that provide for heat exchange, nor the methods that exist for computing the rate of heat exchange. So that's going to be the fundamental difference here. As we move into heat transfer, we will be taking a lot of that into account now. So that leads us now into the discussion of heat transfer. So the discipline of heat transfer specifically seeks to quantify the rate at which heat is exchanged through rate equations. So this is the quantity of the rate in which heat is exchanged. So that's important right there. We're quantifying it now when we're dealing with heat transfer. So examples of some equations that we're going to utilize for this are equations 1.2, 1.3, and 1.7 back in your textbook. And these principles are still going to enable you as the engineer to implement these concepts of thermodynamics that you've seen in your previous courses. So we'll take a look first here at equation 1.2 from our text. Now this shows us here that our heat flux is equal to our thermal conductivity times our temperature difference divided by the length times our K value here. And again, our K value is our thermal conductivity times delta T over L. So all this is saying here is we can either write it out individually as T1 minus T2, and this may become important if we're talking about different boundaries, surfaces, fluid, where that might be for T1 and T2. In general terms, though, it is K, our thermal conductivity, times the change in temperature over the length. So that is equation 1. Now, another relationship for our heat flux here is going to be this is equal to our H value, which is the convection heat transfer coefficient, times, again, the change in temperature here, but now it's specific with these temperatures. It's saying T sub S, and if we come over here, our T sub S is our surface temperature, and T sub infinity, which is going to be the free fluid temperature there. So the difference between our surface and free fluid temperature right there, times our H value, our convection heat transfer coefficient, is going to be equal to our heat flux. So this relates back to equation 1.3 from our textbook. Now, if we go to 1.7, our heat transfer from radiation is equal to Q over A, as we plug into those guys there, where A is our area there. And this is equal to our epsilon E sub B times TS. Now, let's break each of these down before we go any further. What is our epsilon value? So we can come over here. Our epsilon value is going to be our surface emissivity. So this is going to be a value between 0 and 1. So we can plug that in down here for our epsilon right there. And our E sub B, or our emissive power, now this is for emissive power of a black body. E is just our emissive power, but emissive power of a black body, which is our perfect emitter. So that's E sub B right there, times T sub S, which we already defined as our surface temperature, minus alpha G. So what is our alpha term? Our alpha term is our surface absorptivity. And this right here, again, is still between the values of 0 and 1. For our alpha term there, times our G, which is our irradiation term right there. And this is equal to, again, now that same epsilon value right there that we discussed before, times our sigma. Now, what is our sigma? Well, if we go over here, our sigma is our Stefan-Boltzmann constant, and we have a value for that right there, times our surface temperature to the fourth minus our T surround, our surrounding temperature to the fourth as well. Now, with an equation as complex and intricate as this, one thing that's going to be very, very important is doing a unit analysis now. So take a look. What are our units here that we should end up with in the end? Well, this is for heat flux, so this should end up with watts per meter squared in the end. And we can go through all of these, take a look at the corresponding units for everything, and make sure they double check. And things like this where you're talking about length and temperature, are you putting those in the right units? Are you using meters, inches, centimeters? Are you using degrees Celsius, degrees Fahrenheit? What are the temperature, what are the units you're using for each individual variable within this? Plug it in, double check, do out your unit analysis, and make sure everything works out as you would expect it to. So that's a great way to double check your work. One, to make sure you didn't miss plugging in anything, and two, to make sure you are using the right units. So next we're going to move on to our conservation of energy, or the first law of thermodynamics. Now this becomes a very important tool within heat transfer analysis. So oftentimes you'll be providing the basis for determining the temperature of a system utilizing this. So alternative formulations, well, this is going to depend on what type of problem you're dealing with here. So if you're dealing with a time basis right here, this could be at an instant or over a time interval. So this is something that's going to be very important for you to really determine from the problem statement, all the given information. Are you dealing with this at that instant in time or over a certain time period? And if so, what is that? What instant in time is it? Is it 3 seconds into the process, or is it from time 3 seconds to 10 seconds within the process here? So understanding your time basis is going to dictate which type of formula you use and what you plug in for that time basis. Now for the type of system, this is something else you really want to pay attention to here is, are you dealing with a controlled volume? In 3 dimensions here, or are you dealing with a control surface? And that's going to dictate how your equations, what formulas you use, are going to vary. So now I want to take a little bit of time and review the first law of thermodynamics. So what is the first law of thermodynamics? Well, this simply states that the total energy of a system is going to be conserved. Now, if this is true, that means that the only way that the amount of energy in a system, can change is if it crosses its boundaries. So now the first law also tells us the ways in which the energy can then cross the boundaries of a system. So if we take the simple case here for a closed system or a region of a fixed mass, there's only 2 ways. Heat transfer through the boundaries and work done on or by the system. And that's kind of important there, work done on a system or work done by the system. We'll get into that in a little bit more detail in a little bit. So what this does is this then leads into the first law for a closed system, which is familiar if you've taken thermodynamics before. You've seen this plenty of times. You should have seen this relationship here where you have our delta E ST total is equal to Q minus W, where I've defined down here each of the variables within that. And as a side note, this is something that is important to do. If you're using a governing equation when you're solving one of your problems, either for a homework problem, sample problem, group project problem, exam, it's always a good idea for yourself and for the person grading your work, or in the real world, somebody who's actually going to be following through and reading your work, to go down and define what each of the variables are for you here. So right here, we can say that our delta E ST total is going to be the change in the total energy stored in the system right there. So the TOT relates to our total on the top here. The ST relates to our stored in the system there, and E relates to energy, and our delta relates to the change. So this is something that's important. And a lot of times this one's defined, this is a common one used in the book, but there may be times where you need to define labels, indices for your variables. And this is important to do, is one, clearly label what they are, what you use them for, and make it something that makes sense. So when you read through, okay, yeah, that makes complete sense as to why this notation was used. Now the Q within our governing equation here is going to be the net heat transfer to the system. This is going to be to the system, where W is the work done by the system. So is it going to, or is it done by the system? That's something that's important here. So this is the way we define this as our Q and W as related back to our governing equation here. Now we can see a visual representation of this. Here's our stored energy right there. And this is equal to, again, our Q, the heat transferred to the system. So you can see that arrow coming in there with our Q, and the work done by the system. You can see our arrow leaving our boundary right there, and our W there. So that will lead us into control volume here, and we'll take a look at an application for a control volume. Now we discussed time before and why it's important. So let's just say here we're going to deal with an instant of time right now for this specific example. And one thing to note as we take a look at this diagram here, that's given a figure up here, the representation of the system by a control surface is represented by a dashed line at its boundary. So you can see that dashed line going all the way around here for the control system. Now we can see here we have our E dot in and our E dot out over here, where this is our surface phenomena. E in and E out, this is the rate of thermal and or mechanical energy that's going to be transferred across the control surface due to heat transfer, fluid flow, and or work interaction. So again, there's our E in and E out. We can relate them back to our diagram up here, going into the system and then out of the system right there. Now on the inside here, we can see we have our EG dot and our EST dot. So what are those? Those are our volumetric phenomena here. So if we take a look first at our E sub G dot, this is going to be the rate. So the dot right there shows the rate of our thermal energy generation. So E sub G is thermal energy generation. And this is going to be due to conversion from one form of energy to another. Examples for this could be electrical, nuclear, chemical. This is an energy process that occurs within the system. So you can see there's our system control right there. So this is all within the system right there. So sometimes a visual representation is very helpful for a lot of this. Now E sub ST dot is, again, the dot represents our rate of change here of E energy ST storage in the system. So this is the rate of change of energy storage within the system. So now within this section, we're talking about the conservation of energy, the fact that energy needs to be conserved here. So we relate back to our textbook equation 1.12c, and we can see here we have our E dot in minus our E dot out plus our E dot G right there. So again, if we can go back up here and say, okay, yes, E sub G dot right here, this is my rate of thermal energy generation there. This is equal to the change, d over dt, of, and that's with respect to time right there, d dt, so with respect to time, first time derivative of EST right there. So we can, that is then equal to the rate, our dot. So you can see right here, there's no dot with this EST here. The dot comes from the rate, which is the change relative to time, or the first time derivative. So a little bit of calculus coming into play here with our conservation of energy equation. Now, again, unit analysis is very, very important, especially when we start plugging in equations within equations or some more long involved equations. We really want to pay attention to units. So we take a look at this here. So each term within this is going to have the same units of either joules per second or watts, depending which ones you're dealing with. And if we think of that, a joule per second makes sense because this is a derivative with respect to time, or a rate with respect to time here, so joules per second, which is a watt. Now that was for an instant in time. What about over a time interval here? So it changes slightly, so it's no longer the rates here, those are no longer dots here, so it's just E in minus E out plus E sub G right there is equal to our delta E ST. So in this one here, each one of these is going to have a unit of joules rather than joules per second because it's no longer rate, it's not relative to time. This relates back to equation 1.12b in our textbook. So let's take a look at a special case right here. And we're going to notice that throughout the semester there's going to be a lot of special cases. And with the special cases, some of our governing equations will be able to be simplified down and modified to match those cases there. So here we're going to talk about the transient process for a closed system. So we're going to stay with this closed system here. It's going to have some mass given to us as m, assuming heat transfer to the system, inflow, and work done by the system, outflow. So another way to look at those. Heat transfer to the system is going to be called our inflow. Work done by the system is going to be our outflow there. Now let's take a look at our governing equations related to that and the same diagram that we've seen before over here on the left. But let's look at it first over a time interval. So if we go over a time interval, that goes back to this equation right here, 1.12a in our textbook there, which is Q minus W is equal to our delta E storage total. So again, our Q is going to be, if we look down here, the net heat transferred to the system, and our W is going to be work done by the system. So our W is our outflow, and our Q is our inflow, as related to our definition up above there. Now, for the special case here, for negligible changes in potential or kinetic energy, if those are considered negligible, whether it's stated in the problem or you've inferred that from whatever project you're working on, then we have this relationship here that Q minus W, or our inflow minus our outflow, is going to be equal to delta U sub T, which is also known as the internal thermal energy. So our delta U sub T is our internal thermal energy there. And this is just for the negligible cases when there's negligible changes in potential or kinetic energy. Then let's take a look at now, we looked at already the time interval. What about at an instant in time? So at an instant in time, we can now deal with rates here. We can say lowercase q minus our W dot for our work rate dot right there is equal to the change in our thermal energy with respect to time. And that's, again, internal thermal energy. So now let's relate this to a practical application here. It's an example problem. And I won't go through the solution to this now. We just want to discuss how we'd set up the problem and how we can take information from both the problem statement and the given diagram here. In the second section, module 2.2, we will go through in a little bit more detail and solve some of these problems out, and I'll show my hand solutions. But for this one here, let's just get it set up. So in this problem here, we have example 1.4, and they give us a long conducting rod. Now they tell us our diameter is up capital D. They also tell us that our electrical resistance per unit length is given to us as Re prime, and this is initially in the thermal equilibrium with the ambient air and its surroundings. So this equilibrium is then going to be disturbed when an electrical current of I is passed through the rod. So we come down here, there's our electrical current I that's going to be passed right through the rod. They are asking us now to solve for or develop an equation that could be used to compute the variation of the rod temperature with time. So we're looking for a relationship and equation to compute variation of the rod temperature and time during the passage of this current I there. So this is all stuff that's going to become very important. There's a lot of information given within the problem statement. We have dimensions, diameters, how things are related, what we're looking for in the end, is it relative to time, all that information there. Plus we have this entire diagram given down here so we can see, okay, this is the diameter D that they're referring to in the problem statement here. Here's our surrounding temperature. I have my ambient air temperature out here, my T sub infinity and my H value there. I have my E dot out that we've already discussed, leaving this. Internally, I have my storage and my E sub G right there, and I know that we're dealing with this dimension here of this length there, and it has some temperature T there. So all that information is given to us. Where do we go from here as we start solving one of these types of problems? So what I like to do is I redraw out the diagram. So right here, I've just copied it over. So you can see this is the diagram I've drawn out. This is the title. So this relates directly back to that format I talked about that I'm expecting for the homeworks and exam problems here. There's the name of the problem. Up here on the right, you'd normally have your name and the class and the due date up there as well. Then we write down our given information. So we read back through that problem statement and we look at this given diagram. We write this all out. This is a lot easier to view when we're coming back and solving through the problem than to try to reread through that problem statement and look at the diagram every time and then decipher it. So this makes it a nice, easy, organized method for you to relate back to all this. So I have my variable name and what it physically is. Now, if they'd given me unit values, I'd also have the value there and the units as well. But for this one here, we just have the variable name and what it actually is. So D is the diameter of the rod. Maybe in the future they tell us it's a value of 2 and units of inches, something like that. So that's something you would also include in your given section if they'd given it. In this case, they didn't. RE, what is that? Well, RE, this is going to be our electrical resistance. What is I? I is going to be our electrical current. T sub infinity is our air temperature, and we can relate back, and it's always good to look back at our diagram. Okay, there's my T infinity there. There's my electrical current coming into the rod right there. Then we go down here, our T surround, or surrounding temperature right there. Okay, there's my surrounding temperature up here, and I have T is the rod temperature. That's pretty clearly labeled right there. There's my T for the rod temperature, and L is the length here of the control volume. So that right there, again, there's our dotted line that represents a control volume right there. Now, the next thing I want to do is in the problem statement, they told us what they were looking for, what they wanted us to solve for on this problem. So in this case here, I write out my find. What did they ask for? They asked for an equation. They're actually looking for a relationship and equation. You don't have numeric values, so they're looking for this relationship in the form of an equation for the variation in rod temperature relative to time. So as we think about how we would solve this problem, we can go back to some of the governing equations we discussed. I have my diagram here. I can quickly reference back to that first page with all my givens and my information for what they're asking me to solve for there and start applying some of this. So now that I look at all the given information, understand what they're asking me to solve for, I need to come up with what are my governing equations that I'm going to use for this. So I take a look down here and I recall, okay, I had my E sub G dot there. I can see that that's right in the center. This is my rate of thermal energy generation due to conversion from one form of energy to another. And I have my EST right here, my E dot ST, which is the rate, again, the dot right there, the rate of change in the energy storage of the system. So those are my two internal parts right there. So this is going to involve change in thermal energy for an incompressible substance there, because we have air up here, so this is incompressible right there, so we can infer that from our diagram as well. Now we can need to come up with our general governing equation to solve our problem, and that's what this is right here. So we have instant change in thermal energy. So d dt is our change right there, our instant change. We go back to that governing equation we just solved for before, or showed before, of u of t right here. And this is equal to mc dt over dt. So d over dt, lowercase here, is a change relative to time. T is my temperature right there. C is going to be my specific heat. M is going to be my mass. So we have everything that we need now in a governing equation right there. And then what do we know about this? Well, the heat transfer is from the conductor, our negative Q. And generation may be viewed as electrical work done on the system, or a negative W dot. So there's our Q and our W dot. And this again, our Q and W dot, if you recall our other governing equation right there, that was for an instant change in thermal energy. So now we've talked about a closed system. Let's move on and talk about an open system. So steady state for flow through an open system without phase change or generation. So a simplified version of it there. But we have this generic diagram here. We have an open system. Well, what's the main difference when we're looking at our diagram here? Well, you can see now for the open system, we have this going on here. So this is going to change our governing equations substantially. So again, let's take a look at this first at an instant of time. So at an instant of time, we have this governing equation, which is given in our textbook as 1.12 D. So we have m dot, or our mass flow rate, times u of t, which is the thermal energy per unit mass, plus our PV down there, where we have P as our pressure and V as our specific volume there, plus our V squared over 2, where capital V is going to be our volume there, plus GZ, where G is acceleration due to gravity, and Z is our height right there. Now this is going to be plus again, now our Q over here, or our heat transfer rate, minus that same m dot, our mass flow rate right there, times again that same U of T, which is our thermal energy per unit mass, plus again that same PV, plus our volume squared over 2, plus GZ there. This is our out there for this section here. And this is all going to be minus our W dot is equal to 0. W dot is the rate at which work is performed right there. So we can see we have this term up front here for input. So we have all that there. And we have our out over here in this term there. And at the end, we have the rate at which work is performed, minus W dot there. So this relates back again to equation 1.12D in our textbook. Now again, with equations like this, unit analysis, please pay attention to your units. Make sure you're plugging in the appropriate ones and double check those. So let's break this down into individual parts within the equation here. So this PV right here, our pressure. So if we come over here, I've got a little cheat sheet for you over here. Our P is our pressure, and our lowercase v is our specific volume. So our PV is known as our flow work right there. And then we have our enthalpy term right here, which is our UT plus our PV. So there's our enthalpy term right there. For an ideal gas with a constant specific heat, we have the following relationship here that we can use to plug in right here. E in minus E out is equal to C sub P, where C sub P is the specific heat at a constant pressure. So again, it told us it was a constant pressure because we're dealing with an ideal gas, times T in minus T out, which is our temperatures. Now, if we're dealing with an incompressible liquid here, we have the following relationship over here now, where we have our U value right here, in minus U out, or thermal energy unit per unit mass right there, in and out, is equal to C, which again is our specific heat, times our change in temperature between the in and the out there. So we can push this down here. We can also see this relationship, our PV in minus PV out is approximately equal to 0, where PV again is that workflow up there. And again, P, pressure, V is going to be that specific volume there. Now, for the case where we have a system with significant heat transfer, we can again make a little bit of more of an assumption here. And this is saying that these terms right here are V squared over 2 for the in minus the V squared over 2 for the out is going to be approximately equal to 0 for systems with significant heat transfer there. So these are all things that we want to pay attention to when we're reading through the problem statement. Make sure we understand if it just tells us, hey, this is an incompressible fluid, or hey, this is an ideal gas, or it's air, so we know it's an ideal gas. Things like that are going to help us simplify down some of these more complicated governing general equations. So the next topic I want to take a look at here is the surface energy balance. Now this is a special case for which no volume or mass is encompassed by the control surface. So this brings now to our conservation of energy equation. For an instant in time for this, relating back to equation 1.13 in our textbook, we have the relationship here that our E dot in minus our E dot out is going to be equal to 0 under our conservation of energy. Now this is going to apply for steady state and transient conditions. Now with no mass and volume, energy storage and generation are not permitted to the energy balance, even if they occur in a medium bounded by the surface. So as we take a look down here at our diagram, we can see our control surface right down here. And this is a control surface with no volume or mass. So we can see it's just this two dotted lines right there that represent that have no mass or have no volume associated with it. And now we have this diagram here. So we have our surface, our temperature over here, our T1. Our temperature at this point over here on the other side of our control surface is T2 right there. And on the outside over here, we have our fluid over here, which has its associated properties here. And we have our surrounding, our temperature of the surround right here with this wall some distance away over there. We can see we have our heat flux from radiation, our heat flux from convection right there, and our heat flux from conduction right here, all going through that control surface right there. So considering all of this here, by conduction, convection, and radiation, we have this following relationship here as related to the variables that we see in our given diagram on the left right here, that our heat flux for conduction minus our heat flux for convection minus the heat flux for radiation is equal to 0. So then we can start plugging in for this here, and we can say, okay, well, I have relationships for conduction, convection, and radiation heat flux right there. We plug those in. We have our K times our T1 minus T2 over L right there. So our change in temperature over the length right there times the thermal conductivity is equal to minus our H value times the temperature difference between T2 and T infinity. Now let's take a look now. Before we looked at this governing equation, we really didn't relate it to a practical diagram. So what is our T2? What is our T infinity? Well, here's our T2 right there. Here's our T infinity right there of the fluid and surround right there. If we go back to the first part right here, we have our K value right there in T1 and T2. There's our T1 and T2. So if again, we're dealing with conduction, this whole term right here deals with conduction with T1, T2. There's our conduction term right in between those two. So that makes sense. Then we deal with our convection term right here. So if we're dealing with our convection term, we have T2 and infinity. There's our T2, there's infinity, T infinity right there. There's our convection term right there. Then we have our radiation term over here, which again deals with, here's our radiation here, the same T2 surface temperature there, minus the T of the surrounding temperature over here, if we're dealing with radiation right there, and there's our Stefan-Boltzmann's constant as well. So once we plug into that general equation there for each of those, we say that this is still going to be equal to 0. So now let's go back and do a little bit of a review here on our first law analysis. So for the methodology for first law analysis, on a schematic of the system, represent the control surface by a dashed line. So our control surface right here is represented by this dashed line for this closed system over here on our schematic. So other thing that's going to be important when we're doing these problems here is choose the appropriate time base as in at an instant or over a period of time. So make sure we choose that, or if it's identified within the problem statement what they're asking us for or what they're giving us for that information. Next, we want to identify relevant energy transport, generation, and storage terms by labeled arrows on our schematic. Is it work in, work done on the system, by the system? So we can see that up here. There's our inflow, there's our outflow right there. There's the arrows pointing going into the system. There's our arrow pointing going out of the system. And here's our variable right here for our storage term inside the system there. Next, from there, we're going to write the governing form of conservation of energy, apply for our specific problem that we're working with any modifications or special cases for that conservation of energy term. Now, there's going to be multiple terms within this conservation of energy. Make sure we do the substitution of the appropriate expressions, just as we showed on the previous slide there, for the terms of the general energy equation. That's something that I really like to do. Rather than throwing one big, huge, long, complicated equation right out at the beginning, and maybe being a little bit wrong because I plugged the wrong stuff in, take a step backwards. Find the general governing equation. Start out with that really simple general governing equation, and then for each term within that, break it down. solve it out separately. It's going to make your life a lot easier as you're going back and trying to solve it and looking at your work, and also for somebody else who's looking at your work, either the grader who's trying to understand what method you were using when they're grading your homework or exam problem, or it could be a coworker or one of your group project partners. Going to make sure that it's clearly labeled and you've defined each step along the way as you're plugging into these governing equations. So start with that really general governing equation first and expand on it from there. From there, take a look. What are my number of unknowns? What are my number of known values? And do the number of unknowns match your number of equations? So do I have 2 equations, 2 unknowns, 1 equation, 1 unknowns, or do I have 3 unknowns and only 2 equations? How do I relate those there? So take a look. What are your unknowns? What are your relationships between all of those? Plug in order to solve for whatever they're asking within the problem. So what I want to do now is move on and talk a little bit and review the second law of thermodynamics. So a real quick recap of it here. The second law of thermodynamics is often going to be invoked when there is efficiency is of concern within the problem statement there. Now this can be expressed in a variety of different but equivalent ways, and we'll see that as we start working through a couple different problems. The second law of thermodynamics is going to be about the quality of the energy when we're dealing with our second law here. So energy is transferred or transformed as this occurs. More and more of it is wasted, and there's a natural tendency of any isolated system to generate to more disordered state. So the second law of thermodynamics is an important tool in allowing us to determine how heat transfer affects the efficiency of energy conversion. So we talked about how we're utilizing the second law when we're interested and concerned with efficiency. So for this one here, let's consider a reversible heat engine, but in the first case here, we're going to neglect the heat transfer effects between the heat engine and the large reservoirs. Now, if we do that there, we can calculate efficiency using Carnot efficiency relationship here from equations 1.15 and 1.16 in our textbook. And what we have is this relationship here where our Carnot efficiency is equal to a W over a Q in, which is equal to 1 minus our Q out over Q in, or this is also equal to 1 minus Tc over Th. Now what are Tc and Th? Well, these are going to be the absolute temperatures of the large cold and hot reservoirs respectively. So we can plug in those there. Now this is something right here, and we're looking back at this, we need to determine what they've given us in the problem statement, what they're asking us for. If they're asking us to calculate efficiency, what did they give us? Did they give us something that we can calculate our work in and out? Did they give us these temperatures, the absolute temperatures of the large and hot cold reservoirs? So that determines which of these relationships we can utilize when we're solving for that. Now let's consider a different case here for an internally reversible heat engine with heat transfer to and from those large reservoirs now accounted for properly. So this is going to give us equation 1.17, or the modified Carnot efficiency right there. So we have the same relationship right here. W over Q in is equal to 1 minus Q out over Q in there, which is equal to 1 minus lowercase q out over lowercase q in here, which, if we come down here, note that these Q out and Q in are the heat transfer rates in units of joules per second, or watts right there for these guys here, which is equal to 1 minus T sub Ci and Thi right there, which are going to be the absolute temperatures as seen by the internal reversible heat engine there. So let's take a look at this as an actual diagram. So we can see here down in the bottom left, I have this drawn out over here, and you can see there's our high temperature reservoir on the top. There's that low temperature reservoir on the bottom. So we can see how we relate these variables. We talked about our Tc and our Th for those hot and cold reservoirs right there. Well, there's our Tc, our cold reservoir right there, the low temperature reservoir on the bottom. Here's our Th, our hot or our high temperature reservoir at the top. Now we can see our Q in is related to our equations over here, our Q in up here on the top right there, our Q out going down there. So we go from the higher temperature to the lower temperature right there through this reversible, internally reversible heat engine right there. So there's our Q out down here at the bottom there. We can see our W value going out right over here. And now we can see our T sub Hi and T sub Ci, again, for the internal temperatures right there. That we can see related back to our diagram. So this is something that's important to do. Not only do we want to read through the problem statement and try to gather as much as information as we can from that, what's written out to us and given to us in that statement, but then relate that and see what more information we can gather from the diagram. A lot of times in these problems, it's great to have both of those available to us. And this is something you should think about as you're thinking about your group project for the end of the semester, where you really do want to not just only give a diagram where it's just overwhelmed with variables all over the place. or just give a very wordy problem and no visualization. Having both of them and having information that overlaps between them. Maybe the diagram gives a little bit more, a few things that you don't see, maybe some dimensions and things like that within the problem statement. And maybe the problem statement gives a couple things that you don't see in the diagram as well. But between the two of them, it really gives you a whole picture of the entire problem and what they're presenting as a system and what they're asking you to solve for. Now, continuing on with the solution to a problem like this and how we would actually solve this, we'll take a look at our heat transfer resistances associated with, in this case for this example here, walls separating the internally reversible heat engine from the hot and cold reservoirs. So let's take a look right here. You can see there's this right here what they're referring to as those walls that are separating the internally reversible heat engine, so here's our internally reversible heat engine right there, from the hot and cold reservoir. So there's your hot reservoir up top here, your cold reservoir down here. So these walls are shown right here, the low temperature side resistance from the wall there, and the high temperature side resistance related to that wall right there. Now, how do these relate to the heat transfer rates and the temperature differences? Well, we have this equation here that is given in our textbook as 1.18, both A and B, where we have that TH minus THI. So there's our TH, the temperature right here at this surface, on the top of that wall that they're calling it, separating those, and THI, which is on the inside right here, closer to the internal reversible heat engine right there. The difference in those two temperatures is equal to this relationship right here. Now the same can be said if we're dealing with the cold side down here. There's our T sub C, there's our T sub C, I for the internal right there on both sides of that place, separating the internally reversible heat engine from the low temperature or the cold temperature reservoir. Now this R sub T term that we're looking at right here for both the hot and the cold side, this is that heat transfer resistance that we're talking about right here. Now, if we're talking about reality versus an actual problem in the book, these heat transfer resistances, again, unit analysis is important here. This is going to be K per W here. These must be non-zero. The reason for this is because according to our rate equations, for any temperature difference, only a finite amount of heat may be transferred. So from this here, now we can come down to this modified Carnot efficiency equation we talked about earlier, and this may ultimately be expressed in the following way here, as related back to equation 1.21 in our textbook right here, where this modified Carnot efficiency is equal to 1 minus our T sub C. So if we relate back to our diagram down here, here's our T sub C down there, by our cold temperature reservoir right here, all over our T sub H, which is up here, and our high temperature reservoir right here, minus our Qin times our TOT, where this is going to be the total internal heat transfer resistance there, where that is equal to, if that's the total right there, that's the sum of both the hot and the cold, so that can be plugged in down here. But this is, like I said, when I talked about it earlier, of having a more simplified general equation here, rather than writing this all in and making it complicated, you can call it R total and off the side say R total is equal to this. It really helps show your methodology and your approach and your solution. It also simplifies these equations down so they're not overwhelmed with tons and tons of variables. Now we can modify, simplify, and plug into these equations right here. So if we go from this equation 1.21 in our textbook right here, now we can see that Nm is equal to Nc, our modified Carnot efficiency is equal to our Carnot efficiency, only if this R of T could be made infinitely small right there. So that right there, if this were infinitely small, this would convert back to our other relationship for our Carnot efficiency. Now for realistic situations, as we mentioned here, this R total cannot be equal to 0. So in reality, this can't go back to 0, so we're going to have to use this modified Carnot efficiency cycle. So if it's not equal to 0, then this is going to be less right here than our Carnot efficiency there. Now this is why good heat transfer engineering is going to improve the efficiency of heat engines, because this is a reality situation. How do we do that becomes the biggest question as we start designing some of these systems.